Alright, the other day we were looking at confidence intervals with two proportions, and now we're going to look at hypothesis testing in two proportions. Whoa, Mr. Cho, like, is there some kind of pattern? Like, are we doing confidence intervals and then hypothesis test, and then another confidence interval, and then another hypothesis test? Maybe. Yeah, we're definitely having a pattern, and you'll probably see this going over and over. We're going to do another confidence interval, and then another hypothesis test, another confidence interval, and another hypothesis test. So brace yourselves. But for now, we're going to look at hypothesis testing in two proportions. So what's the purpose of hypothesis testing with two proportions? Well, you're going to be able to tell yourself, I can test the difference between two sample proportions and to see if it is significant using a two proportion z-test. So again, it sounds very similar to a hypothesis test with a single proportion. Before then, we were taking a sample proportion and comparing it to a population proportion, but now we're comparing two different samples. So like a sample from a boys group and a sample from a girls group, and seeing if there's like any difference, like maybe a sample from Len Camp versus a sample from Knox Central, and seeing if there's any difference. So this is very similar to hypothesis testing with one proportion. So if you need a little review, check with a one prob z-test video. Most of it is pretty similar, like the same logical ideas play through, but there are some differences. So let's start by looking at this example. In a random sample, girls were less likely than boys to say that they are easy to find online from their online profiles. Only 19% of 325 teen girls with profiles say that they are easy to find, while only 28% of the 268 boys with profiles say the same. Are these results evidence of a real difference between boys and girls? Perform a two proportion z-test to discuss what you find. So, with any hypothesis testing, we start off with our hypothesis. And for two proportion hypothesis testing, we have two new sorts of kinds of hypothesis tests. Our null hypothesis would be that P1 equals P2 because we're assuming there is no difference. So if there's no difference, they should equal each other. Like, 2 equals 2, 5 equals 5. There's no difference between 5 and 5, and so we can say 5 equals 5. So if there's no difference between P1 and P2, they should be the same thing. And with that, there's also possible alternative hypothesis. Either P1 just doesn't equal P2, maybe P1 is greater than P2, or maybe P1 is less than P2. Again, same ideas apply. The null hypothesis will always have an equal sign, and the alternative hypothesis will always be not equal to, greater than, or less than. So for example, the hypothesis would be HO, the probability of the proportion of girls, the proportion of boys equals the proportion of girls. HA, the proportion of boys, does not equal the proportion of girls. And remember, you have to define what each one of these proportions are. So P boys is equal to the proportion of boys who say they're easy to find on the internet, and P girls is equal to the proportion of girls who say they're easy to find on the internet. And with any hypothesis test, of course, we have to state our assumptions. So our assumptions, the three big ones always apply, 10%. So the boys and the girls have to be less than 10% of the population. Random, it has to be random, and large counts. So that way we can make sure that we're getting an equal, we're at least getting some people who are easy to find and some people who aren't easy to find. But since we're working with two groups, now we have another assumption. So our new assumption is that the two sample proportions are independent from each other. So remember what independent means. The probability of one thing happening doesn't affect the probability of something else happening. So boys who are more easily foundable on the internet doesn't affect the probability of girls being more easily foundable on the internet. So then our assumptions for our example then are the randomization. The sample of boys and the sample of girls were randomly chosen, as it was said. Next, we have the 10% condition. So 268 boys and 325 girls are certainly less than 10% of all the boys and all the girls online. I mean, it just makes sense. The independent groups are new one, remember, because our samples are random, we can assume that the boys' perceptions are independent from girls. And success failure conditions are large counts. There's 62 successes and 263 failures. For the boys, there are 75 successes and 193 failures. And they're all greater than or equal to 10. So all of our assumptions pass, and so that means we can conduct a two proportion z test to see if there's a difference between the two samples. So with our hypothesis and our assumptions, next comes calculating our z-score. Our test statistic looks real crazy, but it's not. So we have z equals p hat 1 minus p hat 2. So that's just your proportion of the first sample and the proportion of the second sample minus each other, divided by the square root of p hat times 1 minus p hat times 1 over n1 plus 1 over n2. So whoa. We have a P1 and a P2 in our numerator, and we have just a P hat down in our denominator. So what's the big difference between the two? Well, P1 and P2 specifically refer to each of our proportions, so our proportion of boys and the proportion of girls, while our plain P hat down at the bottom is sort of a pooled together version of both our statistics. So we take the number of successes from the boys added to the number of successes to the girls, so x1 plus x2, and then divide that by the sample sizes of each. So it'd be x1 plus x2, all divided by n1 plus n2. So we get this huge, crazy, not actually a huge number, but we have we're assuming that they're equal, right? So because we're assuming that they're equal, when we add them together, the proportions should still be the same. Like, if we're assuming that each is 0.5, it shouldn't really matter if we pull them together, because if we pull them together, they should ideally, in a magical stat world, equal 0.5. So that's why we have to add it together, because we're assuming that they're equal. We just, well, like, hey, if we're assuming they're equal, like, hey, let's freaking just add them together. Like, like, what the heck? But like, Mr. Joe, like, that's a crazy formula. I know it's a crazy formula. But don't worry, it's on your AP Stat formula sheet. So that special case when P1 equals P2, right there near the bottom, that's going to be your standard deviation. And remember, when we calculate our z-score, it's observed minus expected divided by our standard deviation. So our standard deviation, again, is square root of p times 1 minus p times 1 over n1 plus 1 over n2. And remember what we just said, what p actually is. An easy way to remember which one, there's two of them in there, but and when it says a special case when P1 equals P2, we use the one that we were just talking about. And because, so like, when do we assume that? Well, like, when you're doing the null hypothesis, we're assuming that P1 equals P2. So that's why we can use that special standard deviation. So now let's calculate our, test statistic. So we have 75 plus 62 divided by 268 plus 225, and that equals 0.231. Plug in a bunch of our numbers. P1 is equal to 775 divided by 268, and P2 is 62 divided by 325. So we subtract those two, and then divide that all by 0.231 times 1 minus 0.231 times 1 over N1 plus 1 over N2. So you see where everything fits in. If we just, click back here, you can see N1 is our sample size again. Our P1 and our P2 are the sample proportions we gathered about the boys and the girls. And the P hat down in the bottom is just the number of successes the boys plus number of successes of the girls, all divided by the sample size of the boys plus the sample size of the girls. And so from there, we can plug our Z into a normal CDF. We can then draw our Z-score into a normal curve, and we can use that to find our p-value. So wherever the Z-score lands is our p-value. And so we get our Z-score when we, plug and chug all this into our calculator. It's a lot, but we can do it. So when we plug and chug all that into our calculator, we have a P of Z is greater than 2.59. So there's a 0.0048 probability of the difference between boys and girls being that big. And so one thing that I forgot to mention is that because it's two-tailed, when it's two-tailed, so when it's just not equal to, we multiply by 2 to get a p-value. We multiply by 2 because it's two-tailed, so it can be on either side of it. And so because it can be on either side of our normal curve, we multiply by 2 because there's, two, it could be either greater than or less than. So we have a p-value of 0.0096. And so just like any other conclusion, we, say it just like because our p-value, yada, 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 is yada, 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 we yada, 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 our null hypothesis. There's not convincing or there's convincing evidence to say that there is not or is a difference between our context. So for example, because our p-value of 0.0096 is less than alpha equals 0.05, I reject the null hypothesis. There's convincing evidence to say that there's a difference in the proportion of girls and boys who say they're easy to find online. So that is our very own two-proportion z-test. So if you're feeling comfortable, try out example 2 on your own, but I really encourage you because, hey, you're the advocate for your own future. And so you can only advocate for your own learning. I trust you to do that because you're in a college level class. So example 2. A study published in the Archives of General Psychiatry examined the impact of depression on patients' ability to survive cardiac disease. Researchers identified 450 people with cardiac disease, evaluated them for depression, and followed the group for 4 years. Of the 361 patients with no depression, 67 died. Of the 89 patients with minor or major depression, 26 died. Among people who suffer from cardiac disease, are depressed patients more likely to die than non-depressed people? So think about that. Try and again, I encourage you to try answering this on your own. If you need help, look at example 1 and use that as the example to guide you through. But for now, let us move on. So hypothesis. So again, last chance. Try this on your own. Pause the video and try it on your own. So our HO is going to be PD equals PN, and our HA is PD is greater than PN. So PD is a proportion of people with cardiac disease who are depressed, and PN is a proportion of people with cardiac disease who are not depressed. So we're assuming that the proportions are equal, but we're using this test to see if the proportion of people with cardiac disease who are depressed are more likely to die than the proportion of people with cardiac disease who are not depressed who died. God, that's morbid. That's so morbid. So our assumptions. Again, try this on your own. Use the assumptions from the last equation to check out this. So, is it random? Yes, both are random selected. 10%, 361, 89 are less than 10% of the population of people who have cardiac disease and depressed, and who have cardiac disease and not depressed. Large counts. 67 is greater than 10, 284 is greater than 10, 26 is greater than 10, 89 is greater than 10. So that those three check out. And independent, because they are randomly selected, we can assume they are independent. And now we need to look at our test statistics. So again, I encourage you, pause the video, try this on your own. First thing, we need to calculate our p hat. It's going to be x1 plus x2 divided by n1 plus n2, and that is equal to 0.207. So we're just plugging in numbers. We're just plugging in numbers right now. And then we calculate our z-score, which is then just p1 minus p2, so the probability of people who died, who are depressed, who also have cardiac disease, God, that sucks, minus the people who lived, who are, or the people who died who have cardiac disease, but they aren't depressed, so that's nice. We're going to divide that all by our square root of p hat times 1 minus our p hat times 1 minus n1 minus 1 minus our n2. So good stuff, good stuff, good stuff. And that equals 2.22. So then we take that 2.22, look it up. What do we do with that 2.22? We put it, we plug it into our normal CDF, and we find that in order to get 2.223, there's a 0.013 probability of that happening. And so because of our p-value equals 0.013, because our p-value is 0.013 is less than alpha 0.05, we reject the null hypothesis. There's convincing evidence to say that the depressed patients who suffer from cardiac disease are more likely to die than non-depressed ones. Gosh, that's morbid. Anyways, have a nice day. Good night.